Hello, my name is Andy Schweitzer, and this is a video on what I commonly refer to as the mole concept, or calculations involving moles. First of all, what is a mole? Well, one mole, is kind of like 1 dozen. It is just a mathematical relationship. And of course, I've said many times, we always talk about these relationships. Well, if 1 dozen equals 12, it doesn't matter what you're measuring for that matter. It's a way of taking 12 things and squeezing it down into one. So you could buy 10 dozen donuts or 120 donuts. It doesn't really matter. You could have a dozen basketballs, you could have a dozen kids. It doesn't really matter what you're measuring. It's a way of taking number of particles into another way of saying number of particles. They mean the same thing. So 1 mole equals 6.022 e to the 23rd things. And I put things in here. This is also things. This is also a dozen things. It doesn't matter what you're measuring. You could have a mole of donuts, and you could calculate out how long it would take you to eat a mole of donuts. But either way, why do we have these things? Well, it turns out that particles, okay, atoms, ions, molecules, even the biggest protein molecules are extremely small. These guys are extremely small. In fact, 1 mole of water, let's say H2O, has a mass of 18 grams, therefore has a volume of 18 milliliters, and could easily be cupped into the palm of your hand. This is equivalent to 6.022 e to the 23rd particles of water, equals 18 grams or 18 milliliters. So a mole is extreme way of taking a large number of particles and simply scrunching them down to a smaller one. Just like a dozen does for 12, this does for 6.022 times 10 to the 23rd things. Okay. Now, why is that? Okay, and I think it's similar to why we use miles, okay, versus inches. In reality, if you're traveling to Milwaukee, it is equivalent to 100 miles. But inches would work just as fine. It'd be somewhere in the tens of thousands of inches. But why do we need to have miles when inches work just fine? It turns out that humans, okay, humans just tend to work better with smaller numbers than ones that are very large. So we can have a smaller number with a larger magnitude of unit than to have just essentially a very, very large number we're dealing with. It means the same thing. They're the same equivalents. But our brains just happen to work best with things that we can wrap our visualize numbers that are more are smaller essentially. And in reality, we have on our body, okay, we have 10 fingers, and it seems like people actually tend to like with things that are close to around 10, just the way our brains are wired. The farther we get away from that small number to bigger ones, the harder is our brain to wrap a mental image around how many there actually are. So, with that said, it's the same exact thing. So any calculation that we do with inches, we can do with miles. Same thing vice versa. So what is this mole thing going to work off of? Well, first of all, a mole can be converted back and forth to numbers of particles. Now, when we're dealing with numbers of particles, we're dealing with, let's say, something like this, a water molecule. In this case, this is called a molecule. Okay, so numbers of molecules is one thing that we might have. We could have, let's say, some ions. They might call it an ion. This actually would be called a hydroxide ion. Okay, an anion per se. Or we could maybe say we have it simply a simple element. Let's say gold, like a gold particle, AU. Okay, in this case, because it's just a particle, an atom, we just call it atoms. So the most common things that we would deal with as far as particles would be atoms, ions, and molecules. So that would make sense that since it's simply a 1 to 6.022 e to the 23rd linear relationship, that we also would have moles of molecules. So that's spelled real well, moles of ions, and moles of atoms. Okay. It just means the same thing. I can have 2 moles, or I could have 12.044 e to the 23rd actual particles. If it's 2 moles of molecules, I'd have 12.044 moles of or particles of molecules, say the atoms or atoms here. Either way, these are equivalent. Okay. Now, because this is simply a linear relationship, we could easily just use a linear ratio. x1 over y1 equals x2 over y2, where we have 1 mole equals 6.022 e to the 23rd equals, and then we just simply plug in we want. This would be a conversion to flip back from either moles to actual particles. Okay, so it goes back and forth, and it's just like multiplying and dividing. But for the most part, we will use factor label for this. So if I have 1.5 moles of, let's say, hydrogen molecules, then how many actual particles is this? All right, so then dot line, get rid of moles. All right, so again, we have 1.5 moles. Grab my marker here. And when you want to convert this thing to number of particles, in this case, it'd be a molecules, and that's just by describing the type of particle. It doesn't really have anything to do with the actual mathematics. 1 mole to molecules. 1 mole equals 6.022 e to the 23rd, and you would simply multiply these two values together and get your value in molecules. If you want to take say 3.011 e to the 23rd atoms of silver, then you would simply divide by this value. This would be atoms goes on the bottom, and number of moles goes on top. 1 mole is equal to 6.022 e to the 23rd. This particular value, this number, this ratio has a name. It's called Avogadro's number. Sometimes you'll hear someone refer to Avogadro's number, and they're referring to this value right here. Divide it out, and that actual mathematics is 0.5 moles. Now, when you deal with the size of values that we deal with on our human scale, it is pretty much impossible to deal with things on the particulate level. So let's do calculations involving moles. Okay, so doing a mole calculation is much more common than doing a particle calculation. In fact, a particle calculation, like we did previously, is kind of a hypothetical calculation. If I were to do, again, let's say C4H10 plus O2 yields carbon dioxide and water, balance, 4 carbons, 10 hydrogens would be a 5. 5 plus another 8 is an odd number, so I'm going to double this to 8. This will become an 8. This will become a 10, and 10 plus another 16 is 26, and we get a 13 right here. So now, let's just say I have 5 moles of each of these. These represent number of particles, and these number of particles can be utilized as far as limiting an excess, determining the quantities produced in the endpoint, initial, stoic ratio, ending. All of the mathematics of limiting excess can be done with moles as well as with particles. In fact, it is more common to be done with moles because of the fact that this is more along the size of a sample we might use being a human being. Now, equal quantities, faster rate, therefore this is my limiting reactant, and everything is going to be based off of the O2. This will tell me how much I need of this, and this will tell me how much I will produce of these two items. Mathematics-wise, let's go ahead and punch this out. For our need, 5 moles of O2, get rid of the O2 and go to the C4H10 at a 13 to 2 ratio. 5 divided by 13 times 2, 5 divided by 13 times 2 is 0.76 moles of butane, C4H10, that is needed. So this is go minus 0.76. This is going to drop to 0, and that's reflective of that ratio. This is going to be essentially 4.24 moles. That's the excess. And then here we go 13 to 8 and 13 to 10 ratio. I'll just do this quickly. 5 moles at a 13 to 8 ratio. This is going to be CO2. 5 times 8 divided by 13 equals 3.07 moles of this guy. This is going to be 3.07. I can jump from here to here, 8 to 10, get rid of the 8 moles of CO2 and go to 10 moles of H2O. As long as the number I'm using was originally based off the limiting reactant, I can use it. I could even use this 0.76 to jump to the CO2 or the water. And this value is going to be times 10 divided by 8 equals 3.84 moles of H2O. 3.84. Otherwise, that's your example involving a mole-to-mole calculation. Once you've done and you're in moles, of course, anytime that you want to get out of moles, you can easily just do a Avogadro calculation back to either from moles to molecules using Avogadro's number, so you'd multiply by that. Or if you happen to be in atoms, you could divide by Avogadro's number to get back to moles. Easily flip back and forth using a linear relationship of the Avogadro's value ratio. Thank you very much.